Hello guys, welcome to another problem solving session with Special Maths Academy. Jaifi Obukome Jaifi here, and today we're looking at problem 4 of the recently conducted IMO. I think ended some days ago on the 16th. It's a geometry problem. This IMO was held in Oslo, Norway, 2022 IMO, and problem 4 goes like this. Let ABCDE be a convex pentagon such that BC equals DE. Assume that there exists a point T inside ABCDE with TB equals TD, TC equals TE, and angle ABT equals angle TEA. Let line AB intersect CD and CT at points P and Q respectively. Assume that points PBAQ occur on their line in that order. And let line AE intersect lines CD and DT at points R and X respectively. Assume that points ROEAS occur on their line in that order. Prove that points PSQR lie on a circle. Oh, problem is pretty long. Lie on a circle. So that's our problem for today. The problem is actually very long. Yeah, so like how many lines? 1, 2, 3, 4, 5, 6, 7, 8. 8 lines. But that does not actually mean it's too difficult. It just requires some elementary techniques. So I'll be going to a new slide now because I'll be solving the problem there. I already drew a diagram for this somewhere else. Okay, so here is the diagram for this problem. You can see the diagram, right? Everything we need to do this is already on the screen. I've already drawn the diagrams, so you can see the points. Okay, sorry. The point B was omitted. It should be somewhere around here. Okay, so you can see points A, B, C, D, E. You can see points. Any equal line segments are shown by colored lines, like lines with the same color. So you can do this. This is according to the problem statement, so you can see all this. So we want to prove that P, Q, R, S lie on a circle. This is what we want to prove. Prove that P, Q, R, S lie on a circle, right? So let's get down to it. As with any geometry problem, we all know that the first step to a geometry problem usually is to try angle chasing stuffs. So you can see that these green angles, they are actually equal, right? So suppose that they told us the green angles are, suppose the angle T BA is equals to angle AAT. Okay, suppose the green angles were each theta respectively, something like this. Yeah. Okay, then let's angle chase. Then the next thing I want you to do is like consider some triangles now. Consider triangles DET and triangle, okay, BC. Yeah, these two triangles. Okay. So consider these two. You can see that these two triangles, we have that the problem to those that DE is equals to BC, ET is equals to CT, that's their magnitudes, and okay, sorry, and DT, yeah, take this out, don't night, and DT is equals to and DT is equals to TB, yeah. So this means that these two triangles are actually congruent. This means that triangles DT and triangle BCT are congruent. They're congruent triangles. So that means they're like actually the same thing. So supposing I call this place alpha, then this automatically becomes alpha. This is from the properties. Congruent triangles are basically the same. They have the same angles. So if this is something like V, then this should also be V, right? So we're all good on that. So then the next thing we do, we can angle chase here. This is 180 minus V minus alpha. Angle ESD is 180 minus, from some of the angles in the triangle, 180 minus V minus alpha. Then similarly, this other angle here, we also know that angle CQB is 180 minus, okay, let me write it from triangle QC so we don't get lost, so we don't have to think too much. This is from triangle EDS. Okay, so angle CQB is 180 minus theta minus V minus alpha. Okay, the same thing here. This is like 180 minus theta minus V minus alpha. So the next thing we want to consider now is if you are observant, you can like notice some kind of similar triangles going on. I'm going to clean this first part now. Cleaning all this. And so kind of similar triangle stuff going on here. So let's just see what those triangles are. This problem is actually very interesting. The author was really a good note, so I tried. Maybe this could be something like cheat one, shortlist or something. Cheat three. I don't really know. Find that next year anyway, when the shortlist comes out. So yeah, so like I said earlier, there were some similar triangles. So let's actually identify those similar triangles. Okay, so now consider these two triangles. Consider triangles QTB and triangle, okay, yeah, STE. So if you can notice, angle CQB is equals to angle EST 180 minus theta minus E minus alpha. Yes, minus theta, yes, sorry. And angle CBQ is equals to angle SET, which is equals to theta. So we know these two angles are equal. So that means the last one now means that angle QTB has to be equals to angle ETS, which is 180 minus 180 minus theta minus V minus alpha plus. So this is something like okay. Yeah, so this is something like V plus alpha. So these two are equals to V plus alpha. So automatically, since these three triangles have the same angles, let me mark the equal triangles. So can see them. Then this equals to something like this. Yeah. I mean, so this means that, what does this mean? This means that triangles QE, okay, rather triangles QBT and triangle SET are similar, right? This is like a similar ratio stuff. Yeah, they are similar. So we can write out the similarity ratio. That means QB over SA is equals to BT over ET, which is equals to QT over ST. So at this point, this ratio, I'll be using this ratio next. So this is we have BT over ET equals to QT over ST, right? So then this means that TS times TB or ST times BT is equals to QT times ET, right? So at this point now, we might want to make some things happen. You know that, recall that TB is equals to T. Let me tell you, pink lines. The problem gave us is the pink lines. So this means that TS times TB is equals to TS times TD, right? Yeah, since TB equals TD. Then the next thing is okay, let me come up, let me clean some of this section. When the part will no longer work. Okay, so we know that TS times TB equals TS times T. So let's just like box these parts. Then look at the second part. We know that we have QT times ET. We know that the problem told us that ET equals to TC. The blue lines. So I'm just putting this so you can like know why this is going on. So this means that QT times ET is same thing as QT times TC. And we know that, so I'm going to rewrite this backwards. And we know that this is TS times TB, right? And then we know that this equals to TS times TD. Let me do this so you can like see why this is going on. And this is TS times TD. This is TS times TD. So this means that this is equals to QT times ET, which is QT times TC, right? That means TS times TD equals TQ times TC. So this is actually very good because since TS times TD equals TQ times QC, then from converse of power of a point, from the converse of power of a point theorem, a point, we have that D, S, Q, and C lie on a circle. Let me clean this other part at the bottom. That's what this ratio implies. So, and now we have one circle now. Our things are actually cool. So, at this point, you might start a mini celebration. So, we have one circle now. So far, so good. We know that DSQC lie on a circle. So, let's just see what this DSQC is all about anyway. So, I'm just going to do like a sketch of it. So, this is D. Something like what we have. This isn't this last edge. Okay. I'm just trying to like show you where that DSQC circle is. So, okay. So we have that DSQC lies on a circle. Yeah, this is good because then this means that so like let's join Q to D. Join Q to D. Sorry about the lines there. So since DSQC is cyclic, I'm just trying to sorry about the lines. Since DSQC is cyclic, like the line on a circle, then that means angle QSD equals angle QCD. Why? They both lie on the segments QD. Yeah, you can say that from angles on the same segment theorem in a circle, so circle geometry stuff. So what does this mean? So let's suppose I call this place X, right? And this entire setup here becomes 180 minus theta minus v minus alpha plus x, right? Then this place here also, this other place, let me use blue. This blue section, this is so this becomes 180 minus theta minus v minus alpha plus x as well. Okay, so we know that so let's use this now. So we have that angle QCD equals 180 minus theta minus v minus alpha plus x, right? Then the next thing, we're almost at the end now. Like, this is my favorite part of geometry problems, or any problem solving generally, when I'm almost killing the problems. We're almost at the end. If you're observant, you can see how this will end, but let's just complete it. So I'm cleaning these sections once again. Okay, so we know that from exterior angles theorem, in triangle BPC, we know that angle BPC plus angle CBP, that's this angle here. Let me use this. Okay, this is yellow, is not the best. So let's just say here, we know this angle here, this what I'm coloring green, and this other section, they are like equal. So these two are like, okay, if I say equal, the sum of these two has to equal this outside, this blue section. So this angle BPC plus angle CBP is equals to angle ECD. This is from the exterior angles theorem. Then we know this. We don't know this, but we know this. We know this is 180 minus theta minus alpha. So this is coming from sum of angles on a straight line. 180 minus theta minus alpha. Then we know angle TCD. This is okay. What else? Okay, what else am I missing now? Okay, not just TCD. Sorry, this is not actually TCD. Sorry, there was an error there. It's actually BCD. Oh, this should be equals to BCD. This kind of things actually happen, but it doesn't actually change anything. Angle BCD, right? And we know that this BCD, it's this entire angle. BCD is okay. Let's say BCD is angle DCT plus angle TCB. You can see this is BCD, and this is angle DCT is what we already have. 180 minus theta minus v minus alpha plus angle TCB is v. This is 180 minus, okay, plus x, rather there's plus x here. So this v like cancels. This is 180 minus theta minus alpha plus x. So we have that so let's just write it out so that we don't get. So angle BCD is 180 minus theta minus alpha plus x. Okay, yeah, so this is good. Then we know that angle CBP is 180 minus theta minus alpha. So I come back to this identity now. This okay, this theorem, this exterior angle theorem stuff. Then I like substitute. So I have that angle BPC plus, in place of angle CBP, I put 180 minus theta minus alpha is equals to 180 minus theta minus alpha plus x, right? So this stuff like cancel out. So we now have that angle BPC equals to x. So this angle here is x. Okay. So this is angle. This angle is x actually. But this is good. How is this good? Because if this is x, the problem is done, because then if you are observant, if I join Q to arrow, then you can see something now, right? There are many ways to conclude, but this is just the best way. Once you can show that, then now to finish at this point, you can say we're done because it's actually over. Then can I say since angle CPB is equals to angle ROPQ, and this angle ROPQ is equals to angle ROSQ equals x, then ROPSQ all lie on a circle. This, so we see that this they're all lying on the circle, so you can see why. You know this angle ROPQ equals angle ROSP means that there's a segment that they lie on the circle. Lie on the circle. Okay, sorry, they all lie on the circle. And they are subtended by this chord ROQ. Angle ROPQ and angle ROSQ are subtended by segments. Okay. By segments ROQ. So these points, so this means that this circle actually does exist. So I was supposed to like prove the existence of this circle. So since these two angles are equals to x, let me just show you this. Since this, okay, let's use another color to prove it. Since this and this, they are both equals to x, then you can see like they are somewhere here. So that means they lie on the same circle. So all lie on the circle, and we're done. So that's just all for this problem. Pretty interesting, right? Yeah, that's how IMO problems are. Just some. So what did we really use here? We just used some angle chasing, then some clever lens chasing and other things, and we got the result. So that's how you do an IMO problem. So stick around, more problem solutions will be coming soon. In the meantime, you can interact with the remaining solutions on this channel. Obukome Jaifo from Special Maths, and goodbye.